Physics has to do with movement. And we're not just talking about cars moving and trains moving and bicycles and people. There's more to it. We could be talking about the movement of sound. A lot of instruments have vibrations and they're moving. It might be about electricity, where we're talking about electrons that are moving through wires, and how does that work? It might also be talking about mechanical. How does potential and kinetic work? That has to do with physics. In today's video, we're actually going to be taking a closer look at things like position and displacement, velocity and acceleration, and how they look on a graph. Let's start off first with position. Where are we? Where are you? We might say, hey, I'm located at this address. That's a position. That works out great for somebody that knows the area. But a position might also come down to, hey, it might be a GPS coordinate, longitude and latitude. We talked about kind of in class where geocaching has to do with finding a specific location where something is hidden. There's a really fun kind of app where you can do that. You can find locations around you, find a neat little treasure, but it has to do with position. Now, if I'm going to a friend's house, I might say, hey, I live at this address, which is close to maybe that middle school, or maybe that bank, or maybe that playground. That's using what we call a reference point. Think about it. If I'm moving in regards to something. I'm moving down a street, past houses. If they weren't there, are we actually moving? So a reference point is simply something we are comparing ourselves to, maybe a location, or our motion or movement. Now, position has a lot to do with movement. Think about it. If I change my position, say for example I'm on a football team, I'm on the 20-yard line and we move to the 25-yard line. Think about it. If we changed our position, we have moved. Now, two things come up. We have distance and we have something called displacement. Take for example the distance. Say I go to my friend's house and I travel down the roads, I make left turns, right turns, I go up mountains, down mountains, and I travel a distance of 2 miles to get to a friend's house. Okay? Displacement has to do with what's the change in position. Okay? The start was I was at my house, and then the end point was my friend's house. If I draw a straight line going through houses and through the mountains, that would be my displacement, the change from start to finish. Now what's interesting is, think about this. If I started in my house, went to my friend's house, and returned back home, my start and stop are exactly the same. So my displacement would be 0. My distance traveled, that was basically 2 ways. I went there and back. I have to kind of follow the exact path. Now, distance and displacement are only the same if, when I travel in a straight line, and I end up at a different location than where I started. The next two terms we're going to talk about are speed and velocity, and they're very similar. They have to do with the rate at which we travel a distance in a specific amount of time. Take for example, if I'm driving down the highway in a car. If I go 60 miles, which is a distance, in a rate of 1 hour, right, we call that 60 miles per hour. Now, a lot of times we use meters per second. We're talking about science and usually in physics units, but those units can actually change. They could be different. It could be in minutes, or it could be in hours, it could be in kilometers, it could be in feet. So we need to be very careful, but a lot of times we're using meters per minute, just like miles per hour. It's a distance over time. That's why speed and velocity have the same equation, which is v equals d over t, or distance over time. Now, instead of using the v for velocity, we could use s for speed. Now, where is that difference coming from? Think about it. When you're driving in a car, we have what's called a speedometer. It tells you your speed driving. So if I'm driving my car, you might say I'm going 30 miles per hour, 40 miles per hour. That is a speed. If you've noticed, there's no negative speedometer. There's no negatives. There's no negative 20. If I'm going in reverse, there's no negative 20 miles per hour, 30 miles per hour. Speed cannot be negative. So there's no direction with speed. It's simply a rate at which we're traveling. Now, velocity has direction. So that means it can actually be positive and it can be negative. So we're saying if we're going 20 miles per hour in velocity, we're probably going to assume that's forward or towards a certain location, north, south, east, west, maybe towards the mall, maybe around the NASCAR track. Okay, if we have a negative, we're going to make the assumption that's the opposite direction. So maybe I'm moving backwards or in reverse. Maybe on a track, maybe I'm going the opposite direction. Instead of maybe going clockwise, I'm going counterclockwise. So velocity and speed are very similar, except velocity includes direction. So it's like saying, hey, velocity is speed with direction. All right, let's put our equation to the test. So say we have Felipe. He's going to his grandmother's house. It's 180 miles away. That's a distance. And say it takes him 3 hours to travel there, which is our time. So if we take 180 miles, divide it by the time, 3 hours, we end up getting what? 60 miles per hour. Now, if we know what direction, we can make this a velocity instead of speed. So say maybe his grandmother lives northeast. We would say Felipe would have to travel 60 miles per hour northeast to get to his grandmother's house. So there you have it. We use the equation v equals distance over time. The next term we need to talk about is something called acceleration. This is the rate at which velocity or speed changes. So a way to think about that, if I'm at rest and I start running to 20 miles per hour, okay, there's a change in my speed. Now we can see, how does that change work? What's the rate of that change? Okay, and we would use an equation where it's A, acceleration, equals the change in velocity over time. You might see a shorthand for this. There's a little triangle, right? They call that a delta, which is for the Greek letter. So it's delta V, so the change in velocity over time. Another way you might see it written is V2 minus V1 over time. And that V2 and V1, they stand for different velocities. Maybe V2 is the final velocity and V1 is the starting velocity. Okay? So we find that change in velocity and we put that over time. Now, it's very important that when we're doing acceleration, okay, we want to be careful on the change in velocity. Okay, if I say something is speeding up, that's usually what we call positive acceleration. It's a positive number. If something is slowing down, for example, say I'm driving my car and I slam on my brakes because there's a red light coming, I'm slowing down. So what's happening is that change is actually going to be a negative number. So we say it's negative acceleration, or we could say, hey, we're decelerating at such and such rate. Now the units we use, if you take a look at the equation, we have, for example, a lot of times we have meters per second on the very top. So maybe we're doing velocity in meters per second. Okay, remember that's a velocity. Now we have time on the bottom, so what happens is our units on the end of this is usually meters per second squared, or sometimes meters per second per second. So you can quickly identify in a word problem that, oh, this is a acceleration, not a velocity, by just looking at the units. Okay, if it's squared or if you see two division signs, okay, we know we're talking about acceleration. Now let's put this to test. How does this kind of work? What does this actually mean? Say we have a school bus. It's at rest, so it's not moving anywhere. And it speeds up to 80 meters per second. Now I know that's a crazy speed, okay? So say we're going 80 meters per second. Okay, and it took us 10 seconds to get to that rate. So if we were to use our equation, V1 would be 0 because we're at rest. V2 would be that 80 meters per second. And our time would be 10 seconds. So in our equation, we would write what? You write 80 minus 0, and it's over 10. So if we do our math, we get 80 on the very top, right? So it's positive because we sped up. So the change in velocity is 80 meters per second, and it's divided by 10 seconds. So our answer, 8 meters per second squared. Now say that same bus, it's going to 80 meters per second, right? And it changes into, say, a different zone where it's a neighborhood, so they have to slow down. And we went from 80 meters per second to 20 meters per second, right? So our change is 60 meters per second. Now we're slowing down. So we want to say, hey, it's negative 60 meters per second. And say the time it took us to do that was 6 seconds. So again, we would do our equation, V2 minus V1. So it'd be 80 minus 20, and then it'd be divided by that 6 seconds. All right, so what's our answer? That's right, negative 60 over top. And then we have 6 seconds below, so our rate of change is negative 10 meters per second squared. So you see that negative shows that, hey, we're slowing down. All right, hopefully that kind of really helps show kind of what acceleration is. We might play with that equation a little bit. For example, if I said, hey, I have a car and it's traveling 50 meters per second, right? And if we knew that it was going to slow down or decelerate, by 10 meters per second squared, okay, that means that every second it's going to be slowing down. So if it started at 50, 1 second later we know it's going 40, another second later it's going 30, another second later it's going 20. And why? It's because we knew the acceleration. In this case it was negative, we were decelerating, so we knew it was slowing down. For speeding up, it'd be the reverse. So if we knew we were accelerating by 10 meters per second, instead of it going from 50 to 40, it'd go from 50 meters per second to 60. So again, it's showing the change in velocity or the change in speed. Now, your favorite part. This is where it comes to graphing, and this is where, again, it can get a little confusing even for people that have done this a while. So if we are graphing for velocity, so graphing for, okay, this means that we probably have distance and we have time, part of those equations where it's v equals d over t. If we were to do that, our y-axis, so that's the one that goes up and down, that's where we're going to put our distance, okay? Our x-axis, that's where we're going to put our time. So a graph for velocity is distance over time. The neat little thing here is, if we were to graph that, so if we were to graph that, we're going 10 meters in 5 seconds. The slope of that, if you notice, if you remember from math class probably, right, is positive. We have a positive line, a positive slope. If we were to find that slope, think about it. If we were to find the slope, we would divide the distance, the change in the distance, over the change in time. So distance over time, and we would get the slope. The slope of a graph, that's distance over time, is the velocity. If there is a horizontal line on that graph, think about it. If we're staying at one certain distance, okay, we're not moving. Okay, if the line starts going into a negative slope, that means we're going backwards or towards the start, or the opposite direction. Now the next graph we have to talk about is acceleration. Okay, usually when we're graphing for acceleration, we have on the y-axis, we have velocity. So that's that meters per second, or maybe it's miles per hour. On the bottom, we still have time. Those times are going to be the exact same. So if we had two graphs, a graph for velocity and a graph for acceleration, it's the same problem. We're going to probably keep the exact same time increments. We can keep it nice and balanced. Now the size changed. So maybe what might have been 800 meters as a distance on our graph for acceleration, now we're dealing with just the velocities that we have. That might be a very small or very different set of numbers. So be very careful when graphing. So think about it. Now we have velocity on the y, we have time on the x. If we were to find a slope of the line, say it has positive slope, think about it. We would be doing the change in velocity over the time. That's the equation for acceleration. So if we're finding a slope of velocity over time, that slope is going to tell us the acceleration. A positive slope means we're increasing speed. A horizontal line on that graph would show we're keeping a constant speed. Right? Think about it. Velocity is right across from it. So if we're at 10 meters per second and we stay there, it's a horizontal line, we're keeping a constant speed. Now the only thing here is, if that horizontal line is at 0, that means we're stopped. So we need to look carefully at that. And then last but not least, if we have a negative slope, so on a velocity versus time, if we have a negative slope, that means we are slowing down. That does it for today's video. Hope you enjoyed it, and plenty more physics to come.